This experiment is testing different properties of proteins. Proteins are polymers of amino acids that are held together by peptide bonds. The primary structure is covalently linked. There are other superstructures built on this backbone that make the protein active the way you can see it in nature. In a secondary structure of a protein, the original chain can fold back on itself into either an alpha helix or a beta pleated sheet. These secondary regions of structure can be part of the molecule. It's quite common for any given protein chain to have many helical regions, a number of pleated regions, and some irregular ones as well, which you'll see shortly. On top of the secondary structures, we have tertiary structures, which occur when amino acid side chains interact with each other, making salt bridges, disulfide linkages, and other relatively weak but important interactions. To be active, many proteins have more than one protein chain that are tied together in quaternary structure, and prosthetic groups such as metals or light-absorbing molecules make them active. Any disruption of the entire protein structure can cause temporary or permanent inactivation of the protein. Changes in pH, addition of metal that interact with disulfide bridges, addition of organic poisons, heat and cold can all cause inactivation of a protein due to disruption of the tertiary structure. One of the proteins that we'll be using in this experiment that can demonstrate these properties is phycocyanin. This is a conjugated globular protein which has several chains of amino acids along with chromophores. Chromophores are light-harvesting organic molecules. It's part of the photosystem II complex found in cyanobacteria, which plays an important part in photosynthesis that green algae can use to convert sunlight to energy. In its native properly folded state, phycocyanin is a beautiful deep blue color. It also has the additional easily observable property of fluorescence. When light that the chromophores can absorb shines on it, part of the absorbed light is given back out as light. In this case, the chromophore molecules absorb wavelengths of visible light, and the fluorescence is red. So you have two obvious properties to observe in order to decide if the protein structure has been altered. We can use color and fluorescence. Inactivated protein, especially when completely unfolded and denatured, will be yellow and not show any visible fluorescence. Phycocyanin is easily isolated at neutral pH. This will be isolated from spirulina in a phosphate buffer solution. First, started out by weighing out the spirulina, about 0.5 grams, and this was distributed into two different centrifuge tubes. Then try to put them evenly into the two tubes, and then 7 mils of phosphate buffer was poured into each of the tubes. Make sure to mix the tubes up, and it is also important not to crack the tubes on the counter as I did. You may start to see some bluish green liquid spill here and there. There might be droplets, and that's because I cracked the cap of the tube while trying to bang it on the counter. And shaking it vigorously was not getting me anywhere, so I decided to use a spatula to stir it. So the spatula can get all the way into the end of the tips. That makes sure that all of the powder in the tubes is moistened and can be extracted. Next, it's important to centrifuge with balanced tubes. This was centrifuged for 3 minutes. Next, the liquid was transferred into an Erlenmeyer flask using a pipette. The liquid itself is dark blue. When the light is shined on the sample, it turns a nice dark red color. And each tube gets 1 ml of the protein. And we have 8 samples. There's a control, a hot sample, a cold sample, sodium chloride, ethanol, lead nitrate, acid, and base. Dilute the first 3 samples with phosphate buffer. I'm going to put 1 tube on ice for a few minutes. And then I'm going to add 2 mils of sodium chloride to the tube. My water bath is hot now, so I'm going to put that tube in there for a couple of minutes. Next, I will add ethanol to the sample. The next sample is getting lead nitrate. Alright, for the next sample, we're going to add hydrochloric acid first. And now we're going to add 1 ml of sodium hydroxide to the same sample. Okay, next we're going to add sodium hydroxide 1 milliliter. And now we will add 1 ml of HCl to that tube that just had sodium hydroxide added.